Welcome to this lecture series in real analysis. In this lecture, we'll prove the very important but very easy chain rule. And primarily what we need to know is the following fact. Suppose f is a function defined on an interval and a is in the domain such that a is not the right boundary point. Then f is right differentiable at a if and only if there is a map of the sort such that the map is right continuous at a, and this equation holds for all x. So we proved this earlier, and this is what we are going to use. This was basically an equivalent way of stating right differentiability, and there were three equivalences that we had proven. This is one of that. All right. Here are some problems for practice. And now let us get started. Okay, so we are going to prove what is called the chain rule. So what is the hypothesis? Start with two functions, f and g. F is defined on I, g is defined on j, and I and j are assumed to be intervals. Assume that image of f is contained in j. Let me illustrate by picture. We have seen this picture many times. So the first blob denotes I, the second one denotes j. And g is a function from j to the reals. And f is a function with the property that image of it is contained in j, so I can just draw this arrow. It takes all of I inside j. So I can make it like that. And therefore, this composite is a meaningful thing, meaning if you start with a point in I, you push it by f, and then you push it by g. That is the composite. So naturally, the question arises, suppose I know that this is right differentiable at some point, and then this is also right differentiable at the image of that point. So in pictures, suppose I know f is right differentiable at a, and I know g is right differentiable at f of a. What can I say about the right differentiability of the composite function? And what can I say about its derivative? So that's the question that we are going to answer. So a be a point in I such that f is right differentiable at a and g is right differentiable at f of a. And when we have said it, we have already implicitly assumed that a is not the right boundary point, meaning this is the case. Otherwise, there is no question of right differentiability. And similarly, fa is less than supremum of j. Just for understanding, you can take I and j as open intervals or just open sets. This interval hypothesis is not very important. Just assume I and j are open sets. For understanding, that is the best. So we want to show that the right derivative of the composite at the point A, the composite has A in its domain. So we are basically asking what is this value, if it even exists. And the answer is yes, it exists and is equal to that thing. What is that thing? It is the right derivative of f at a multiplied by the right derivative of g at f of a. So it's as simple as it could have been. And the proof is also as simple as it could have been. So we'll just use the criterion that we recalled earlier. So since f and g are right differentiable at a and f of a respectively, we can find functions which is right continuous at a and such that f of x minus f of a equals this expression for all x. And similarly, let b be a function from j to r, right continuous at f of a, such that let me use a different letter. Let me call it y. Right? Just immediate by the hypothesis that f and g are right differentiable at a and f of a respectively. What are we interested in? We are interested in this limit. This limit So what is it? This is equal to limit. We'll just use this formula. So let me change this a little bit. Nothing. So I just brackets. And instead of y, I will substitute f of x. So I will get, this difference is nothing but b of f of x times f of x minus f of a divided by x minus a. And now we know that this limit exists individually. Just forget about that guy for the moment. This exists because f is right differentiable at a. What about that guy? B is a right continuous function at f of a and f is right continuous at a. Why? Because f is right differentiable at a. Right differentiability implies right continuity. And therefore this limit also exists and is equal to b of f of a, and b of f of a is nothing but the right derivative of g at f of a. So first things first, this limit is nothing but the product of the following limits. Right? And this is equal to b of f of a because of continuity or right continuity. And that other thing is the right derivative of f at a. This is equal to that and this is equal to that. Now what is b of f of a? B of f of a is nothing but the right derivative of g at f of a. Why? Because you take this to that side, take the limit by continuity of b, you get that. So this kind of argument we have done before. Not much of an argument anyway. So this is equal to the right derivative of g at f of a. That's it, as simple as that. Let's look at an example. So f is a function which is differentiable. So we have proven the right-sided version, but you can prove the left and the two-sided version. Typically, we are only interested in the two-sided version. So start with a differentiable function, and suppose we define a new function via this recipe. N is some positive integer, or it could even be 0. So we define a new function via this recipe. What can we say about the derivative of this guy? So we all that we are doing is if we let maybe calling it g was a little bit of a bad idea. Let me call it h. Let me call that h, and now we define a new function which is g. G is x going to x to the power n. So then what is h? H is nothing but g composed with f. And therefore by chain rule, the derivative of h at any point, call it a, is the derivative of g at f of a times the derivative of f at a. But we know the derivative of g at any point. G is this polynomial. So we know the derivative of g at a is n a to the power n minus 1. So at f of a, it is correspondingly it is n f of a to the power n minus 1 f prime a. So that's the answer. We didn't need to fiddle around with the limits or anything. Once we have proven this general fact, it's so easy to compute derivatives. So if you have been given a complicated function, try to recognize it as composites of simple functions. General philosophy in mathematics. A concretization of the previous example is, suppose f is defined via this recipe. What is the derivative of f at 1? Now if you expand this out, you can of course compute this. You just expand this out, it will be a degree 12 polynomial, and it will also take a sufficient amount of time, and one is prone to making errors. But if you just use what we just proved, just define f as, f is already defined that way. So I think you get it. I mean, define capital F as this value, and then capital H is capital F to the power 3. So we are interested in the derivative of H. I mean, F power 3 is nothing but little f, so I'm just changing the notation. And we are interested in the derivative of H at 1, but we know this is 3f square at 1. Yeah, this is 3f square at 1, or maybe I'll write it 3f of 1 square, and then f prime 1. That's what we just proven. That's what we proved above. I'm just plugging in things. So what you get is 3 f of 1 is 2 square f prime 1. What is f prime 1? I'll calculate. But before that, this is 12 times f prime 1. So if we wanted to calculate f prime 1, we use the polynomial business. F prime 1 is 5 into 4 into x into 1 cube minus 0. So this is equal to 20. Our answer is 12 into 20, which is 240. And there might be a calculation mistake, but you can fix it. Alright, so this is all that I wanted to say. As usual, like, comment, share, subscribe, and I will see you next time.